I am a research assistant professor here in the geography department. And what I want to talk about today is research that I've been engaged with here at UVM for the past 2 years or so. Initially, I came here as a gun postdoc, and this work has transitioned with me into a research faculty appointment. Generally, my work is focused on understanding the functioning of floodplains. And by that, I mean specifically looking at their capacity to retain sediment and nutrients. And I've also been looking at how their level of hydrologic connectivity controls some of that functioning. This is work that I initiated through a grant Beverly Wemple and I received through the Lake Champlain Basin program. However, we've also received support and funding over time from the Nature Conservancy, EPSCoR, as well as the Institute. And I just want to make sure to thank Beverly Wemple for her help with this work, as well as other collaborators, Kristen Underwood, Don Ross, and Jesse Gorovich. So what I'm going to really focus on is this piece of the hydrologic connectivity today and our effort to map inundation frequency of floodplains in support of understanding this functioning. And so when I talk about an inundation map, I'm showing an example here. I just kind of basically mean what's the spatial distribution of flood events and what's their associated frequency. And so in the next half hour or so, I'm going to talk about kind of why these maps are important, how we go about mapping them, what potential, what are some kind of challenges in mapping, and how we tried to overcome these challenges with a new model, the application of that model to the Lake Champlain Basin, and an evaluation of it, of the mapping. The last minutes, I'm going to switch gears and actually talk about some of the additional work I've been doing at sediment and nutrient retention on floodplains, and then also talk about kind of this larger initiative that my work, as well as those of my collaborators and colleagues, are going towards in an effort called the Functioning Floodplain Initiative. And so inundation maps provide critical information and serve as these really powerful tools to help us address some pressing environmental challenges. Both here in Vermont, these specifically really are challenges for us, but also these things play out in communities throughout the US and around the world. Lake Champlain, specifically here in Vermont, is an impaired water body because of excess sediment and phosphorus derived from surrounding watersheds. And we're really understanding the role that floodplains can play in helping to improve downstream water quality, as well as the numerous other functions. As water accesses the floodplain, it spreads out. We see a decrease in velocities. And so anything in transport, the sediment, the nutrients, any other constituents derived from the upstream landscape settle out onto these floodplains. And so they can serve as these really important sinks for these different constituents. But that assumes that they are hydrologically connected to the river, that there's actually that opportunity for the floodwaters to access them. But what we see is in Vermont and elsewhere, many of these surfaces are disconnected because of general degradation, a history of upstream land use practices, but also because of hard and fast impediments on the floodplain surface itself, berms, levees, roads, railroads, and such. And so inundation maps provide us kind of with this snapshot of what surfaces are hydrologically connected, where there's disconnections, and where there's opportunities to maybe improve upon that. Additionally, these types of inundation maps are really helpful to inform and communicate flood risks. And this is obviously a kind of a moving target on the growing need for this information and for rapidly updating this information, as we know with a changing climate, notably here in the Northeast, as large storms become more intense. And so many of these applications, these conservation and flood risk applications, rely on some existing deterministic maps, and the most prominent of which and the most highly available are those developed by FEMA and available through FEMA in support of the National Flood Insurance Program. And many of you have probably seen these and dealt with these either from your personal property or otherwise. And these communicate the likely extent, typically of the 100-year flood. And so I'm showing you an example here. So what this is communicating to us is it telling us that any land, any property that's within this blue area was within the floodway and is likely to be wet during a 100-year flood, or that flood that occurs once every 100 years. Anything outside, likely to be dry. However, these maps, there's kind of growing evidence that these maps can be inaccurate. There's in the literature, we are seeing sort of documentation of post-flood analysis of which properties are actually inundated and not. They're also tend to be outdated, so not necessarily representing the current hydrology or our current understanding of the hydrology or what's kind of going on the ground. And they're also missing for many communities. The information communicated with this type of map is limited. It's really only telling us maybe potentially what's going on in the 100-year flood, not on more frequent floods or infrequent floods, or as these infrequent floods become actually more frequent. And there's also misleading information. I'll talk about this here in a minute. The information that goes into creating these maps, there's a ton of uncertainty. And with this, you're not really communicating that uncertainty, right? You're actually saying with high precision, or at least you're communicating that this area is wet and this area is dry. Traditionally, these maps are created using hydraulic models. And by that, I mean, it's kind of a general term for sort of a suite of models and tools that we use to understand the routing of water through the landscape so that we can then understand how it interacts with the landscape and the extent of inundation. And these range in complexity and different packages, and there's a whole, but they can be 1D, where depth and velocity are averaged kind of at the cross-section, like in a HECRAS model that might be familiar to many of you listening in, shown here, or 2D to 3D models where we're looking at the depth and velocity at any node on the landscape. And kind of no matter where you are within this, these approaches are really data and computationally intensive. Obviously, there's a huge range, but therefore they're really hard to use to update these maps regularly when there's new information that comes to light, and to bring them to scale so we can look at these kinds of this information over large scales. And so in response to this, we've seen kind of a new generation of lower complexity models. And by that, I mean, these models really simplify the process or simplify the governing equations that describe the movement of water through the landscape. They also kind of become lower in complexity because they coarsen or decrease the resolution of which these governing equations are calculated. So like I showed, you know, at the node is where depth and velocity are calculated in some models, or versus cross-section, but these actually even coarsen it up to a greater degree and look at it at the reach scale, or maybe even coarser, so over 500 meters, a kilometer, or so on. These are often terrain-based and taking advantage of the growing availability of high-resolution data. And this type of model is being developed by a variety of different research groups, different nonprofits, and going into a whole suite of applications. For example, some of them that I just show here on the screen. Anywhere from the National Water Model used to predict, to increase our prediction of flood risk, an ecosystem service mapper that just was published by the USGS, and so on. And so what I want to note here is that 2 of these applications actually take advantage of the same kind of baseline approach. It's a really kind of just a basic approach that's growing in interest and popularity within the last decade or so. And this is an approach based on a hand map. And by hand, I mean height above the nearest drainage. And there's an example of it shown here. And these are relative elevations. And so you basically take an absolute elevation map, or a DEM, digital elevation model, and you map the relative elevations above the nearest channel bottom. And like I said, this has been established. There's some literature on it. People have adopted this basic approach. And we actually adopted too. And so I just want to take a minute to kind of walk through what this approach really means. So the first step in 3 really simple steps. The first step is, again, to convert a DEM, so absolute elevations, into a map of relative elevations above the channel bottom. And so there's an example here. The second is to then use that map to build a stage discharge rating curve for each reach, or again, each unit of analysis. And kind of in our application and many applications, they use the Manning's equation, which is an empirical relationship that takes information about the underlying topography and hydraulic characteristics and uses that to calculate discharge, which is this Q here. And so for each successive elevation above the channel bottom or hand elevation, we calculate a discharge, again, to create the stage discharge rating curve. The third is then to translate that to floodplain maps. And so you need some information on what the discharge is. And so often we use flood frequency curves that relate the recurrence interval of a given flood event or a storm event to the discharge. And so I'm just going to show kind of how we use basically these two curves to create the maps. So if we want to identify a 2-year flood, we identify the discharge associated with it for that reach, use the stage discharge rating curve to see that hand elevation for this reach of about 4 meters is associated with a 2-year flood. We can similarly do that for a 10-year flood and 500-year flood, and therefore kind of build out these flood inundation maps. What we did is we took this hand model, and again, we wanted to apply this to a large scale to understand kind of some of these processes that are going on in the Lake Champlain Basin. We formalized the hand approach, this kind of these basic steps, we formalized it into a Python code and extended its functionality, and we call it the probHAND model. And I just want to take a break here to acknowledge the fact that when I say we formalized it into Python code, it wasn't me at all. It was my collaborator, Jesse Gorovich, who's been really instrumental in taking kind of these ideas and actually implementing them so that we can do this at scale. And so I want to thank him for that. Like I said prior, there are large uncertainties that go into inundation mapping, even using those complex models. And as we kind of simplify process and scale up, those uncertainties become greater. And so we wanted to account for those uncertainties, but also communicate them, right? And so those deterministic maps can provide that false sense of precision, saying this is where it's wet, this is where it's dry. And so we wanted to communicate the fact that we don't know that with such certainty. And so to do that, we incorporated a Monte Carlo-based uncertainty analysis to account for various sources of uncertainty, including limited data, measurement error, process simplification in a variety of those inputs. We defined probability density functions for each of these inputs, ran the model 1,000 times, sampling from those probability density functions to create 1,000 different rating curves and 1,000 different discharge values to sample from those rating curves to basically come up with 1,000 solutions. From that, we then can create kind of these probabilistic floodplain maps or create an understanding of kind of the percentile of those projections. And so this is an example. This is just for one flood event, but showing the distribution of our certainty or uncertainty based on that modeling. And so these dark areas are showing us areas that we are pretty certain, almost exclusively certain, that this will be inundated during a 2-year flood event. As the reds become lighter and become pink, these are areas that might be inundated, but we have less and less certainty that that's the case. So in total, right, these communicate the extent of inundation, but also the associated certainty or uncertainty. And I just want to note that this model, the description of it, the application of it that I'll talk about here in the next few slides, is in a paper that we submitted to PLOS ONE. It's currently in review. So we applied the probHAND model to Lake Champlain Basin in Vermont. And we used a variety of actually almost exclusively publicly available data. And that was one of the goals too, so that this is something that actually can be adopted elsewhere with relative ease. Here in Vermont, we benefit from a great data set of high resolution DEMs derived from LIDAR. And this is growing in availability elsewhere too. We use land use land cover data set, a flood frequency relationship, or these regional relationships developed by Olson. And then NHD plus reaches, which is actually a national data set that defines different reaches. In total, we mapped floodplains for streams with a drainage area greater than 10 square miles. That was the focus of this work. That along about more than 2,000 river kilometers. And we did this at a really high resolution at 1 meter. This is kind of higher than nearly any study that I've seen for this type of work, because we really wanted to make sure to capture all of that information that we have in those high resolution DEMs. But because of such high resolution, it actually did take quite a bit of time to run the model, about 6 weeks, and that's reduced significantly if we actually coarsen the input resolution. We define the probability density functions using by comparing hand model output to a variety of different information sources we have here in the Lake Champlain Basin. And we evaluated the integrity of the model within the Mad River watershed and in the Winooski River Basin. And we did this in two ways. And I'm going to talk about how we value the integrity of it, because none of the kind of solutions are certain either. And so what we're really doing is looking at our approach, but also another approach. And we did that by looking at the output for the HEC model, which is a hydraulic model. And again, we compared that to the HAND model. And so that's kind of shown here, an example. And to evaluate, we calculated an F statistic, which is basically a measure of how well our predictions of wet cells correspond to predictions of the HEC wet cells. And that's, again, this F statistic, where the higher the number, the greater the overlap between those two predictions. A value of 1 would be our HEC model, or our HAND model, excuse me, is in complete agreement with the HEC model. And with the idea here, again, that like this HEC model is a little bit more of a robust way of identifying inundation extents. And so we're just looking to evaluate the two. What we found generally is pretty good agreement between them. On average, we found a value in F statistic of 0.72. And as you can see, these values increased for larger floods. And this is what we expect to see, given the factor, or it makes sense, I should say, given the fact that as you increase for larger floods, the floods take on more of a characteristic of the valley characteristics and less about the underlying topography. It's less sensitive to some of the governing equations that we're simplifying with the HEC model. The second one is that we compared it with surveyed high water marks. And so this is a data set that was collected following Tropical Storm Irene here in Vermont in 2011. So these are on the ground observations of the maximum extent of water on the ground surface. I do want to note that high water marks are typically collected like on trees, on buildings, things that are kind of floating. And when you look at a aerial image, are basically kind of floating in the middle of a floodplain. So we just had to translate those to what we call an edge of water point. And those are shown here with these yellow stars. And what we did is compare the distribution of these to the probability map. So the distributed probabilities of where these flood events are likely to be based on our modeling. And what we found here is this cumulative curve that describes the distribution. And what we found generally is good agreement in the sense that the distribution of probabilities describes well the distribution of these observed high water marks. Finally, we wanted to explore the variability in output to identify where there might be opportunities to improve upon the accuracy of these maps by reducing uncertainty. And so what we're looking at here on this x-axis is the proportion of the variance explained by the different variables that we used in the hydraulic, or excuse me, in the HAND model, where this geom is the hydraulic geometry, or again, what describes that underlying topography that's under the water surface. This N is kind of a tuning factor within the Manning's equation, and that's kind of the governing equation for this model. S is slope, water surface slope, and then Q, Ri is the discharge associated with a given recurrence interval flood. And we did this, and what I'm showing here is for the various recurrence interval floods. And what kind of immediately stands out is this geom variable, right? This hydraulic geometry variable that describes most of the variability here, right? And so we can see that especially when we look at how it's distributed for the different flood events, right? And so this 2-year flood, the geom describes most of the variability in the output. And when you get to 500-year flood, we reduce that variability. And that's pretty consistent with those observations we were making based on the comparison between the HAND and the HEC, where that underlying geometry is more important for these smaller floods. And what I want to kind of highlight here is that this is actually really promising. So the hydraulic geometry is really important in determining the variability in output. And so if we invest in and we look to improve upon those types of inputs and reduce our uncertainty, we have opportunities to improve upon the accuracy of our maps. And there's increasing availability of better underlying topography from things like LiDAR-derived data sets, as well as increasing capacity to actually process it and analyze that data. I also want to draw our attention to this discharge variable here, which describes between 15 and 35% of the variability in output. And the largest amount of variability is in these larger floods. And this is important, right? Because our understanding of flood events is decreasing. Our uncertainty of this is actually growing, especially for these larger floods. And so this is another area we probably want to focus our efforts into reducing that uncertainty. And there's opportunities that are growing, right? We're seeing these remote sensing that are helping us to understand stream flow in ungauged river basins. And we're seeing some kind of unique approaches to then using that to understand kind of flood frequency relationship, again, in these ungauged basins. Additionally, work going towards understanding and making predictions about future stream flows with our changing climate. This slope and roughness here are definitely important, and when there's opportunities to constrain them and reduce uncertainty, we definitely should take those. But these are more specific often to a given area, and they're hard to constrain often unless you have kind of this opportunity to get on the ground and actually measure these variables. And so especially kind of the focus should potentially be on this discharge and hydraulic geometry when we think about kind of improving this kind of effort. And so I'm going to switch gears for the last few minutes or so, again, as I indicated, and talk about this work that I've also been engaged in trying to build an understanding of the capacity of these floodplains to retain sediment and nutrients. So as I mentioned earlier, we know there's great potential, but our understanding is really lacking of what that potential is, what that magnitude is, and what the controls are on the capacity of these floodplains to retain sediment and nutrients during floods. And this is mostly true here in the Lake Champlain Basin, and in Vermont, we have very little data. And so the work I've been engaged in is trying to build that data set and build that understanding. And in 2019, I established more than 180 monitoring plots on 25 different floodplain sites located throughout the Lake Champlain Basin. And those are shown here with these yellow dots. And they're, again, distributed throughout the basin and throughout the Lake Champlain Basin, all the major contributing drainage basins. They're on small rivers, large rivers. They represent sort of a huge environmental gradient of what we see in the basin. Steep gradients, shallow gradients, and so on, different land uses. And each of these plots consists of 4 15-centimeter square artificial turf mats, as shown here. And these are affixed flush with the ground surface, and they serve as surface markers so that floods overtop these plots and sediment and nutrients and organics and all the other constituents that are being transported in these floods are deposited. We can go out and actually identify exactly how much was deposited from a certain flood event. In 2019, we had 3 flood events we were able to collect sediment following, and most notably in November 1st of 2019, there were significant floods that inundated almost all of our plots and put sediment on nearly 75% of them. And so we have a really robust data set. And once we collect that data, and you can kind of see an example of down here of what those plots look like. Once we collect that data, we bring it back to the lab, dry it, sieve it, weigh it, analyze it for total phosphorus. We've also been looking at percent organics and the particle size distribution. And this data set is nearly complete coming out of the lab. And we've had 2 incredible undergraduates working on that and busting their butts over the summer to get that data. And like I said, we're just starting to look at it and looking at the magnitude, but also the variability, and try to kind of tease apart what some of those controls are in those relationships. But for this talk, what I wanted to do is actually bring this back into thinking about this flood inundation and what the controls are on flood inundation and kind of that hydrologic connectivity. And so what I did is I took all of the output from those hand layers. So all of the different flood events we modeled, all of the probabilities, and put that into one variable called an annual probability of inundation. And that's shown here. So these reds are areas that are inundated once every 2 years regularly, right? So these are highly connected areas. The oranges are inundated once every years, and so on. And so I link that with different plots. So for example, if these blue dots are different plots, each of those plots have a specific or a unique, I should say, probability of inundation any given year. And so I took all of the data, because we are getting all that data out from the lab, and I looked at to see kind of what the controls are. And so what we see is that it describes the variability really nicely. That we can see that those areas that are highly connected, so they're active, they're inundated regularly once every year or 2 years or maybe even multiple times a year, have these highest rates of retention. So on this axis, we have the total phosphorus, which is a rate. So how much phosphorus is retained on the floodplain per unit area per year. As we move away to these areas that are more disconnected, aren't inundated as regularly, we see a decrease in that retention. And this is promising for a variety of reasons. It's kind of what we hypothesize how these floodplains should function. But we can also use this kind of in a more specific way in thinking about making predictions about what's going to happen to these floodplains in terms of serving as these nutrient sinks and improving downstream water quality if we do something like improve the hydrologic connectivity. So for example, if we restore the floodplain, we remove an impediment, we make it more hydrologically connected, we can therefore increase the capacity of that floodplain to retain nutrients. And with this information and this data, ideally we're actually coming up with hard and fast numbers too. And this information that we're working towards, this type of analysis, these hand maps, all of it are going into this larger initiative, as I alluded to initially, the Functioning Floodplain Initiative. And this is an initiative that myself, as well as my collaborators and other colleagues here at UVM, are working towards trying to translate our research into a management tool. And Kristen Underwood here at UVM is leading this effort and representing us at many of us researchers, and representing her work too on in-stream processes, along with Beverly, myself. Eric Roy is kind of contextualizing the phosphorus dynamics to an even greater degree. So not just thinking about the particulate dynamics, but actually what happens when these floodplain surfaces are inundated. Sometimes they actually release phosphorus. And so we're trying to put together an understanding and build a bit bigger understanding of that to help inform these restoration efforts, as well as Donna Rizzo. And like I said, this is a multidisciplinary effort. Us at UVM, we're trying to translate this information to create this tool for other stakeholders in the state to use to map and track and understand the functioning of floodplains. This is the core team here, us at UVM, along with Evan Fitzgerald, Roy Schiff, Jody Stryker, Mike Klein, as well as folks at DEC are really spearheading it. But I want to mention that there's a variety of other stakeholders throughout the state. This is really important because this tool ideally is being used by these stakeholders. And so in the process of us translating our science, we're constantly checking in with them to make sure that this is a tool that's useful for them. And this is something that they're going to use kind of in the capacity of identifying restoration opportunities and continuing to track to meet downstream water quality targets, to improve flood resiliency for our communities, and also think about kind of creating habitat. And so with the last kind of minute or so, just to summarize, we've been working on creating this inundation mapping tool and applying it to the Lake Champlain Basin called the probHAND model. And as a result, we create these probabilistic floodplain maps. The simplistic representation of process that we incorporate in this isn't perfect. It definitely is limited in certain areas, like in urban areas, which have a lot of bridges and therefore backwaters. But in general, we're finding that the general patterns are well described by this. And the addition of the uncertainty in the probability maps kind of enhances that as well. Inundation that we've kind of been able to extract out of these types of maps is really important for explaining variability in phosphorus retention on these floodplains. There's a ton of other variability in there, and we're hoping to kind of constrain that even further. But this is definitely a big kind of key piece to it. And then all of this work is really going towards understanding floodplain functioning in Vermont, and using it to again translate this research in a way that other stakeholders in the state can use it to kind of better manage our floodplains. And with that, just want to thank, again, the collaborators I've mentioned throughout this talk. There are numerous. Most of these projects definitely aren't pulled off without the significant help from students. And we had some significant help, a lot of field time, a lot of lab time. I also want to kind of note a variety of other partners that have helped me identify our field sites. It was definitely a tricky effort. Both kind of matching the environmental characteristics with landowner access. And so a big thanks to many of those. And then of course, the funding. And so with that, I'll take questions.
Thank you, Rebecca.
You're welcome. Thank you.
I'd like to remind the audience that you can use the Q&A box and send in the questions, and we'll answer them as best as we can. And so I think I'll go for it. So, my question is primarily, I think, taking a step back. What are, specifically talking about Vermont, what are Vermont's needs in terms of, we're talking about retention of nutrients and phosphorus. So
yeah.
Are we trying to maximize the retention, minimize it, optimize it, or what's the goal for this mapping in the long run? Thank you.
That's a great question. We are trying to optimize the retention. The idea being that if we can keep some of those sediment and nutrients on the landscape before they make it to Lake Champlain, we're going to be improving water quality. Specifically thinking of phosphorus, which is why my work and so much of our work is driven by phosphorus, because Champlain's impaired for excess phosphorus, but we can think of it in other ways too. There's a lot of work now going on to carbon sequestration on these floodplains and how these can serve as sinks for carbon, as well. In other areas that are impaired because of excess nitrogen, we can also be thinking about kind of nitrification on these floodplains. And so they serve as these sinks. And so yeah, we're trying to optimize kind of them as sinks. And not as kind of net exporters, in which there is a component, as I mentioned, Eric Roy's been working on that, of thinking about, for some of these settings, when you actually increase the hydrologic connectivity, unfortunately, you're actually going to increase the release of some phosphorus. And so he's trying to understand kind of where those, where that risk lies, if we actually do improve upon the connectivity.
Great, thank you.
Thank you, yeah.
So Jeremy has asked if you have a sense of how much the problem is simply excess nutrients from farms or fertilizers.
As opposed to other sources, I'm guessing, Jeremy. I don't know. I off the top of my head, I don't know the exact kind of breakdown. It's definitely documented in the TMDL, and others on this call can speak to that in a much better way than I can. And so kind of the source of it, again, it's documented, and I'm not sure, but there's, our work on understanding and trying to improve upon retention of these constituents on the floodplain is just one piece of this larger effort to reduce the fluxes downstream. And a big part of that, again, others can speak to this much better than I can, is better management practices or best management practices on ag fields, on roads, on all sorts of other sources that we know contribute to phosphorus loading.
Okay, so another question related to modeling. So you mentioned using LiDAR, and I was wondering if when you are creating this model for predicting phosphorus quantities in the landscape, so I maybe did not understand it very well, does it consider both the vertical distance and the horizontal distance? Because I think both of them would have different implications on how water spreads. Maybe it's always going from up to down, but on sides it spreads equally.
I don't know if I specifically understand your question, but when we, maybe I'll just kind of address a couple pieces of it. When we use LiDAR in here, which is integral to this kind of approach, Again, we use it to then create this hand map, which is these relative elevations. And the way that the relative elevations are calculated is by routing water through the landscape. So there's all sorts of kind of algorithms that have been established and used for a variety of different purposes. But for this, we route water through the landscape and then calculate basically based on that pathway of water as it moves down, you know, a DEM basically, what that distance is between the bottom of the channel and that surface. And so that's kind of how the LiDAR is used, and that's kind of how the elevations come out. But it is somewhat of a function of its pathway too. And so it's not a one-for-one with your absolute elevations. It's dependent on these flow pathways. I don't know if that helped answer your question.
I think, yeah, I did not phrase my question very well, but you answered it.
No, it's all right. Thank you. Okay, great.
Okay, so let's see if we have other questions. Yes, we do. Okay, so the question is, across your many floodplains monitoring sites, are you seeing any interesting or surprising patterns of sediment or phosphorus deposition related to valley settings, watershed position, or drainage area size?
Yeah, you know, to be honest, I haven't been able to dig too deep into that. That is something I would love to be looking at right now, and it's definitely next on my list. But a kind of a cursory glance, not really. You know, I think what Kristen's trying to get at is, are we seeing kind of, as we start in the headwaters and we go down through the watershed and we get out to kind of the wider valley bottoms, are we seeing kind of a trend? And I don't think so. I think it's more specific to kind of these localized conditions. Slope is absolutely an important part. So if we do think of kind of slope decreasing as we move downstream, that's absolutely important. But the trends there are seemingly largely driven by other variables, and not as much by these kind of, as we would think of, you know, your river continuum from your headwaters down out. And so it'll be interesting kind of once we dig in a little bit deeper, and maybe come up with some more sophisticated ways of looking at this information, if we can tease out some of those trends, which would be kind of cool to see.
Okay, thank you very much, Rebecca.
Thank you, Ali.
So on behalf of Current Institute, I would like to thank you and everyone who joined us online, and want to tell that please join us for our next Current Exchange with Joshua Faulkner from UVM's Who's Talk, Applied Research and Outreach at the intersection of agriculture, climate change, and water quality in Vermont. The talk will be on October 2nd, next Friday. Thank you very much and hope to see you then.
Take care.
Bye.